Have you ever thought about what happens when you just look at something? I mean, in our everyday world, not much, right? But what if I told you that at the smallest, most fundamental level of reality, the very act of looking isn't passive at all? What if it's an interaction that literally changes what you're looking at? Well, today, we're diving deep into quantum measurement, a concept so strange it challenges our entire idea of what reality even is. Okay, think about it like this. In our world, the classical world, looking at something just confirms what's already there. If a coin is on the table, looking at it tells you if it's heads or tails. Simple. But in the quantum world, looking is what creates the reality. Before you measure a particle, it's kind of in a fuzzy cloud of every possibility at once. The moment you look, you force it to pick one. You're not just confirming an answer, you are creating it. And that right there, that's the mind-bending difference we're talking about today. So we got to be clear about what we mean by measurement. When a physicist says that word, they don't just mean passively seeing something. Oh no. They mean interacting with it, poking it, probing it, shining a light on it, somehow forcing the system to give up its secrets. It's the moment that the fuzzy, undecided quantum world has to give a sharp, definite answer. And that interaction, well, that's what changes everything. So how does this whole interaction actually work? It's all governed by two fundamental and frankly shocking rules: the rule of probability and the rule of collapse. And trust me, this is where quantum mechanics just completely leaves our everyday intuition in the dust. These rules dictate the bizarre game we have to play to get any information out of the quantum realm. Let's break them down. Okay, rule number one. You can never know the outcome for sure before you look. Never. All quantum mechanics can give you are the odds. It's like a cosmic slot machine. You know the chances of hitting the jackpot, but you have no way of knowing what any single pull of the lever will give you. You only get to know the probabilities. Now, physicists have a neat way to write this down. For a quantum bit, or a qubit, its state before you measure it is called a superposition. It's a blend of both 0 and 1 at the same exact time. And don't let the symbols here scare you. Those letters, alpha and beta, they're the key. They're just numbers that hold the probabilities for what the answer is going to be when we finally look. So how do we get from those alpha and beta numbers to the actual odds? It's surprisingly simple. You just square them. The value of alpha squared gives you the probability of measuring a 0, and beta squared gives you the probability of measuring a 1. The key thing to remember here is that before we look, the outcome isn't set in stone. Only the odds are. So if you thought the probability part was a little strange, rule number 2 is where things get truly bizarre. The very instant you measure that qubit and get an answer, let's say you get a 0, that beautiful superposition is completely destroyed. It's gone. That whole mixture of possibilities just vanishes. The state is fundamentally and irreversibly changed. This is called state collapse. State collapse is basically the universe forcing a choice. That rich, weird world of possibilities where our particle was a little bit of this and a little bit of that all at once, poof, it vanishes in a flash. The act of measurement snaps the system out of that dreamlike state and into a single concrete reality. All the other potential outcomes are just gone. Okay, let's walk through this whole process from start to finish. We start with our qubit in a superposition, a mix of both 0 and 1. Then we perform the action. We make a measurement. The result is determined by those probabilities we talked about. Let's say, in this case, we get a 0. Now here's the kicker. In the aftermath, the state has collapsed. It is now permanently a 0. If you measure it a million more times, it will be a 0 every single time. The possibility of it being a 1 has literally vanished. Now, you might be thinking this all sounds a bit philosophical, but it's not. Physicists have developed incredibly precise mathematical tools to describe this whole act of forcing a choice. And to really get how they control and predict these interactions, we need to take a quick look at the tools of the trade, something called measurement operators. Think of these measurement operators as asking the qubit a very specific yes or no question. One operator, P0, basically asks, hey, are you the state 0? And the other one, P1, asks, are you the state 1? And here's the thing, you can't ask both at once. When you apply one of these mathematical questions, you force the system to give you a definitive answer. And in doing so, you project that fuzzy superposition down onto that single outcome, which triggers that collapse we've been talking about. So why on earth does all this mind-bending theory actually matter? Well, because it is absolutely central to the incredible promise and the immense challenge of building quantum computers. This isn't just a weird physics quirk. It has huge, real-world consequences for the future of all technology. And this right here, this brings us to the ultimate double-edged sword of quantum computing. The power of these machines, as you see on the left, comes from that superposition, letting the qubits explore a vast number of possibilities all at once. But the problem is that the only way we have to get an answer out is to measure it. And as we've learned, that very act destroys the superposition, ending the quantum computation dead in its tracks. So this leads to the billion-dollar question for every quantum engineer out there. How do you get the answer you need without killing the magic that created it in the first place? Well, scientists, being the brilliant people they are developing some seriously clever strategies to try and tame this collapse. One approach is something called quantum error correction. You can think of it like a protective shield, guarding the fragile quantum information from collapsing because of random noise from the environment. Another key strategy is delayed measurement. This is all about designing your algorithm to do all the complicated quantum crunching up front, and then saving that one destructive measurement for the very, very end, the big reveal. Okay, so let's just pull back for a second and think about what this all means. We've gone from the simple act of looking at something to a fundamental process that appears to literally shape reality. This isn't just a technical problem for computer scientists. It raises some of the deepest questions we can ask about the universe and our role in it. All right, so if you remember anything from this, remember these key points. First, quantum measurement is a game of chance, not certainty. Second, the very act of looking forces a quantum state to collapse and pick a side. Third, this process is both how we get answers from a quantum computer and the biggest headache in designing one. And finally, getting your head around this concept is absolutely essential if you want to understand where technology is headed. And all of this leaves us with one final, absolutely mind-bending question to chew on. If the act of observation is what forces a choice, if our looking is what creates a definite reality, what is the nature of that reality when no one is looking? That's something to think about. Thanks for tuning in.